Hi everyone. Okay, so this week we are going to see Markov chains. Really one of the fundamental tools for modeling environments in reinforcement learning. So understanding this particular concept will allow us to describe state transitions that is really simple and powerful, I think. So Markov chains. Alright, so a Markov chain, mathematically speaking, is a tuple. We're going to define it as a tuple of a set of states and probability matrix. Okay, we are going to come back to this, but let's see a simple example. We have seen the 1D cleaning robot or 1D cleaning agent. Now imagine we have a system that has three different states. Okay, maybe this state, I'm going to call this S0, S1 and S2. Now from the S0, let's call this operation, and S1 I'm going to call it obstacle, operation, obstacle, and end of the operation. So maybe we have an agent moving around. It can be in operation mode, it can hit an obstacle, and it can end up in a terminal state. Now there's a probability maybe from the from S0, there's a probability of, maybe I can use a red, there's a probability of 0.2 to hit an obstacle, and from the obstacle maybe there's a probability to transit to the ending operation of 0.2. From the operation, maybe it can end up in the terminal state with a probability of 0.1. So as I said, the Markov chain describes the state transitions, and we have probabilities here. Now at the end of the operation, from here the agent, if it finds itself here, there's a probability of 100% chance of, it's being here, staying here, and 0 probability of going to the obstacle operation. So really the Markov chain, has allowed us to kind of illustrate the movement from one state to another. Now we have S0, S1 and S2. I have mentioned that this is a set of states. So here we have S0, S1, and then S2. These are our states here. And then the probability matrix, these are the probabilities, is something like this. Something like this. So for example, moving from S0 to S1, S0 to S1 is 0.2, so that's why we have 0.2 here. From S2 to itself is 1, and 0, 0 to all of the other states. Now really this might look simple, but in the next videos when we see Markov Reward Process, we are just going to add another signal here, a reward signal, and from there we are going to see Markov Decision Process, where we add another signal till we get to this dynamic programming and reinforcement and learning. And this concept itself is might look simple, but really very powerful. Alright, so far so good. Now the Markov chains, it satisfies the Markov Markov property So the Markov chain satisfies the Markov property, which says that a future state only depends on the current state and not the sequence of the past states. So in mathematical terms, it is something like this. To get the probability of going to a next state, st plus 1, given that I am in a particular state and all of the states that came before it, all the way to S0, the initial state, that probability st plus 1 can actually be computed like this. Probability of st plus 1 given just st. Okay, now this is a powerful concept. Think of it. What it tells you is that the probability of st plus 1 given all these previous states, st minus 1, st minus 2, all the way to st, is the same as the probability of the next state, this, given just the current state. So in other terms, we can just, these formulas are the same. What we just did was really just cancel this information. We don't need it. So in another terms is the history of how we got to st doesn't matter. All that matters is the current state. This means that transition from the current state to the next only depends on the present and nothing else. Now this is powerful because, especially in modeling, because we only need to keep track of st. This can make computations much more efficient. You don't need to be storing all of this information in memory, for example. Okay, I hope that is clear. Then what I'm going to do next is to introduce episodes. Now, an episode is really more like a sequence of possible states in a system. So for example, here we have S0, S1, S2. And imagine you start from S0. Now a possible episode is S0, the agent, maybe the agent starts at S0, it can go to S1, then maybe it can go back to S0, then S2. S2 is the terminal state. It's also possible that it can start at S0, then stay there, because there's actually an open some probability that switching from S0 to itself. Then from S0 it can just go to S2, and then it terminates. Maybe from S1 it can go to from S0 then to S1, then from S1 to S2, then it terminates. So an episode is more like a sequence of possible states that we can experience. This is important because we will be needing this in the next videos. Alright, so far so good. So the episodes more like illustrate how the agents interact with the environment over time, transitioning from one state to another. In the next video, now we have seen Markov chains, we are going to introduce Markov Reward Processes, which really takes the Markov chain and add a reward signal. So allowing us to quantify how good certain states are, or sequence. So here we have 3 states. Now imagine we have thousands. Some of the states might be better than others, and an agent is navigating many different states. We want to quantify how good some of these states are, and that is what we are going to be seeing in the next video and the actually subsequent videos when we start also seeing other concepts. Alright, so let me know if you have any question in in the comments. And as always, there's going to be a Jupyter notebook associated with this video that you can check out. Thank you.